Okay, welcome back. Happy Friday. Today we are covering theorems about differentiable functions. Today's going to be a little bit unusual in that the stuff that we cover is going to be very theoretical, and you guys are going to be like proving theorems, which is a very like mathy thing to do. Even if this isn't like a proof-intensive math course, I think it's still this is an opportunity for us to at least think a little bit like kind of like mathematicians as opposed to budding engineers, which I think a lot of you guys are. So that's the plan for today. Coming up on Monday, I will hand you take-home quiz number, that says, yeah, the third take-home quiz. You'll turn that in to me on Wednesday. So we'll give that to you Monday. Also, Monday is project check-in day. So let me just pull up the calendars for the two projects. This is the regression project. If you have been following the suggested timeline, then today you have finished all the way up through problem number 16. So you can figure out how far you are from the recommended goal here, but through 16 is where we are hoping you are at this point. If not, then perhaps a lot of work this weekend will get you caught up and in a good position to use Monday's project check-in day effectively. So that's the regression one. And then the rainbow one, which involves quite a bit of reading. As of today, you should, in theory, be up to exercise 21. There are a lot of problems in this particular problem set. Most of them are pretty short, but still a lot of stuff, so there's some time that you need to put in. Any questions on the timelines here or the calendar? Okay, so that's what's coming up. We do have our one and only in-class quiz. I guess that's, what is that? Wednesday next week. We'll give you details about that next week. All right, so, but again, the projects will be due before you know it. November 21st and 24th are the two dates. Okay, so again, we're on page 25, and we'll start all the way up at the top with the daily summary. Haley? Can you read the daily summary? Thank you. Let's go to Levi for number one. All right. So here is the mean value theorem. Given some conditions that you have a function that is differentiable, meaning you can take its derivative, then there's the existence of some number that looks like a variable, the C thing, such that that crazy looking equation is true. So we're just going to translate that crazy equation, and you'll see that it's something very reasonable and pretty easy to remember if you just understand what that equation is really saying. So this f of b minus f of a over b minus a is a calculation that should look familiar. What is that calculating? That's the slope, right? That is a change in y over a change in x. It's the slope connecting what points? Like, do you see the points on the graph here? We're connecting the a f of a point, this guy down here, to the b f of b point, which is this guy over here, right? And so what slope are we finding? The slope of a line that isn't drawn in here. So how about we draw that line in? What's the word for a line that hits the curve twice? Yeah, so this thing right here is the slope of the secant line. Okay. And then it talks about this kind of strange thing, this C. It says there's some number C that's in between A and B, so that f prime at this magical number C is exactly the same as the slope of this secant line. But f prime represents slope of what? The tangent line. We know that f prime represents slope of a tangent line. So what this is saying is that there's some point where the slope of the tangent line, so this is the slope of some tangent line, I don't know where it is yet. So there's some point where the slope of the tangent line is exactly the same as the slope of this secant line. But to say that two lines have the same slope means what's true about them? Means they're parallel, right? Same slope means parallel. So translating one last time, there's some tangent line which is parallel to that secant line. Do you buy it? Do you imagine drawing all the possible tangent lines at all these different points on the curve? We've got infinitely many of these tangent lines. Do you buy that there's one that's parallel to that blue line? Reasonable, right? And so maybe we can just kind of ballpark where that thing is. Go. So to me, it looks like it's maybe somewhere around there. This is the one that's parallel. I'm just kind of eyeballing it here. And so what we're saying is that that guy right there, that dot, is the location of the point C. Right? There's some C in between A and B where the tangent line is parallel to the secant line. Okay, reasonable. We believe it to be true. The picture seems to indicate there's got to be some point in there. Okay, so here's our next reader now. Cameron, in English. Okay, so that's the picture. We're gonna have this quick look at Sketchpad thing. Here it is. Again, it looks really nice, so that means it's not mine. This is, again, due to Audrey Weeks. So here's the idea. We've got a secant line connecting this endpoint right here at A to this endpoint over here at B. So I'm going to draw that secant line, and the slope of that line is 0.8, apparently. And then we're going to imagine taking this point X. This is just some variable point, and that's a little tangent line that's drawn, right? And so do you see that, I mean, do you buy that there's going to be some tangent line, one of these tangent lines here that's going to be parallel to the blue? How many tangent lines do you see that you think will be parallel to the blue? Looks like two of them, right? And so, so there's the first one right there. And then it zips over to find the second one. And that's it. So we've got two different points. One of them is at 1.225, that's this guy. And the other one is at this 2.775. Mean value theorem doesn't say there's only one. It just says there's one, and there could be more. It could be 100. Who knows? Right? But there's at least one. Okay, so let's come back here and take a look at number 2. So that's the mean value theorem. 2, we're going to go to Andy.
Two zombies, both in Hertz, start a race. During the race, Goat was consistently shambling slower than Hertz. What can you conclude?
Okay, so so they start in the same spot, and Goethe is always slower than Hertz. So what does that mean for the entire duration of this race? Goethe is always behind Hertz, yes? Okay, so I guess if we're thinking of these as like distances, then we could say Hertz is definitely always ahead of Goethe. I'm going to throw an equal sign in there. If it happens they're going the same speed, then they could be at the same spot, but probably Hertz is ahead. If not, they're tied because it's at the start of the race. So it's easy. It's not hard to imagine that. Let's go to Kyle, the next part of number 2.
Two zombies, both are in Hertz. During the race, was consistently shambling slower than Hertz.
Okay, so this time photo finish means it's a tie, right? Very end of the race. And again, Goethe is slower. So what does that mean about the entire race? Well, it's a tie. So what can you say about, like, is one person consistently ahead in this race? Goethe is consistently ahead, right? The only way for them to finish at the same spot and for Goethe to be moving slower is that Goethe had to be ahead the whole entire time until that very moment, right? And so in this instance, we could say that Hertz was always behind Goethe until he finally caught him at the finish line. Okay, so it doesn't seem like there's calculus there, but we know that derivative can be thought of as a rate of change. And one of the very first classes we had this semester talked about thinking average velocity and then smushing down to small intervals and talking about instantaneous velocity. So in certain contexts, the derivative is a velocity. It's the instantaneous velocity. So let's go to Brendan for 3. Okay, let's pause right there. G and H are so named, that's why Goethe and Hertz were picked. So G prime being less than H prime, what does that mean about Goethe compared to Hertz? Isn't that what it says? Goethe's rate of change, Goethe's speed is less than the speed of Hertz. So Goethe is slower, which is exactly what was true in the previous problem. And now all we got to do is think about, this whole start line, finish line business. So we're looking at the interval AB. So I guess that means we're thinking of A as being the start of the race and B as being the finish. And so in part I, it says assume that G of A is equal to H of A, meaning they're at the same spot. Are they at the same spot at the start or the finish in this case? Let's G of A equals H of A. So which one is that? Same start, right? Because they're tied at A. And so if they're at the starting line together, then who's going to be winning this whole and the entire race? Is Hertz, because right, Goethe is slower. So Hertz is going to, as soon as they start at the same spot, Hertz is going to pull ahead. So Goethe is behind Hertz, right? All the time. And then looking at part two, it says that G of B equals H of B. So they're at the same spot where? At the finish line. So who must have been ahead the whole time for them to tie at the end? Goethe must have been ahead the entire time because Hertz was gaining on Goethe the whole time. So Goethe must be ahead until the finish line when they finally tie. Okay. So that's how we kind of tied the racetrack principle to the calculus. Okay, so that's it on the demo. On the very next page starts the activity. And you're going to end up proving a lot of stuff. So again, think about building up those math muscles in a different way today. Raise the flag if I can help.